Quantum Gaussian processes, a new frontier in quantum machine learning. Quantum machine learning breakthrough. Gaussian processes open new frontiers. The quest to harness quantum computing for machine learning has faced numerous roadblocks until now. A groundbreaking discovery might change everything we thought we knew about quantum AI capabilities. Neural networks transformed traditional computing, enabling self-driving vehicles, language translation systems, and sophisticated AI software. Naturally, scientists eagerly sought to transfer this revolutionary power to quantum computers, but repeatedly encountered unexpected challenges that seemed insurmountable. In an exciting development, researchers at Los Alamos National Laboratory have pioneered an innovative approach to quantum machine learning by utilizing Gaussian processes, potentially solving problems that have frustrated experts for years. We set out to demonstrate the existence of genuine quantum Gaussian processes, explained Marco Cerezo, who led the Los Alamos research team. Successfully proving this opens doors to innovations and entirely new methodologies in quantum machine learning. The foundation of modern machine learning was built upon the discovery that extensive neural networks naturally converge to Gaussian processes. Traditional neural networks contain millions of computational nodes, or neurons, that make probabilistic assessments of input data, though individual neurons operate randomly without bias. When millions work together, their collective output forms a Gaussian or bell curve distribution, allowing scientists to extract meaningful averages from seemingly chaotic data. The Los Alamos team has now conclusively demonstrated that similar Gaussian distributions apply to certain quantum computing processes, a revelation that could fundamentally transform quantum computing capabilities and applications. Their findings appear in a newly published paper in the prestigious journal Nature Physics. But here's where it gets interesting. The team didn't simply copy classical methods, they created something entirely new. Traditional neural networks belong to a category called parametric models, which function by adjusting variational parameters to learn autonomously. After witnessing their success in classical computing, researchers naturally attempted to implement neural networks in quantum systems, hoping to tackle problems far too complex for conventional computers. However, after extensive investigation, the Los Alamos team discovered that parametric models in quantum environments frequently generate unexpected complications, including what experts call barren plateaus, mathematical dead ends that prevent further progress. The fundamental issue with quantum neural networks was our approach of simply transplanting classical neural network structures into quantum computing environments, noted Martin LaRocca, a laboratory scientist specializing in quantum algorithms and machine learning. This strategy proved more problematic than anticipated. We needed to return to fundamental principles and develop simpler projects, more constrained learning methods that could actually function effectively, while providing certain mathematical guarantees. Unlike neural networks, Gaussian processes aren't parametric, allowing them to bypass many of these obstacles. However, Gaussian processes aren't universally applicable. If data doesn't follow a bell curve distribution, predictions can become inaccurate. To address this concern, the team employed sophisticated mathematical techniques to verify their calculations, confirming that their new methodology was genuinely Gaussian and therefore appropriate for processing quantum datasets on quantum computers. This represents the ultimate achievement in Bayesian learning, emphasized Diego Garcia Martin, the paper's primary author. Beyond being mathematically fascinating, our discovery has tangible practical applications. Consider predicting housing prices. You might begin with an initial assumption that prices follow a simple Gaussian distribution. When provided with observations, specific houses and their prices, we can apply this Gaussian process to update our distribution model and generate more accurate price predictions. As we incorporate more data, our predictions become increasingly precise, a technique known as Bayesian inference through Gaussian process regression. Our research demonstrates that this same principle can now be applied within quantum computing frameworks, and this is the part most people miss. Replicating neural network capabilities on quantum computers has been a long-standing objective in the field. This paper represents years of dedicated research and marks the first mathematical proof of this capability. Since quantum computers remain an emerging technology, this work, like much research in quantum machine learning, remains largely theoretical. However, this foundational research is essential so that when powerful quantum computers eventually become available, scientists will have sophisticated machine learning models ready to tackle some of humanity's most complex and previously unsolvable problems. As part of a broader research initiative, this paper signals a new direction that the team hopes the quantum community will embrace, essentially arguing that researchers should abandon attempts to force classical computing models into quantum machine learning contexts, and instead develop approaches specifically designed for quantum systems. This represents our ongoing mission, Cerezo stated. We need to discover novel approaches to quantum machine learning rather than continuing to pursue unproductive paths by recycling outdated methodologies. Do you think quantum computing will eventually surpass classical computing for all machine learning tasks, or will each have their own specialized applications? Share your thoughts in the comments below. More information: Diego Garcia Martin et al. Quantum neural networks form Gaussian processes. Nature Physics 2025. DOI 10.1038 S41567-025-Z. Citation: Gaussian processes provide a new path toward quantum machine learning. 2025 August 4th. Retrieved 5th August 2025 from https://phys.org-news-2025-Gaussian path quantum machine. This document is subject to copyright, apart from any fair dealing for the purpose of private study or research. No part may be reproduced without the written permission. The content is provided for information purposes only.